Okay, we'll go to the biochemical sedimentary rocks now. These are mostly limestones, and they're made out of the mineral calcite, which is CaCO3. They typically form in warm, tropical, shallow, clear marine waters, clean, warm water near the tropics, and composed of shell debris from diverse communities. So coral reefs are some of our most ecologically diverse habitats on the planet. So there's an image there of little parrotfish gnawing at the corals. And then it's going to look like what you see in this quarry wall here. In the quarry wall, you have layers and layers of limestone horizontally deposited, and these little mounds are their reef structures. There are other kinds of limestones, not just reefs. Here we have a fossiliferous limestone that is made out of the hard parts of marine organisms, and just they've deposited maybe on the sea floor and cemented together by other calcite. Chalk is a deposit of tiny little organisms, and they can form big, massive units of it, like these that are making up the cliffs. Macritic limestone, is a limestone mud. So it's a mud that forms on the seafloor out of calcium carbonate. Chert is a different chemistry. It's silica, SiO2, and these cherts here in this image are just different colors. Chert, silica is quartz. And so these organisms that have silica as their hard parts or their seashells, their shells are like little microscopic plankton that just float around the sea. And when those die, the shell of them, that silica shell, is deposited on the sea floor in layers and forms these cherts. Coal is the remains of terrestrial plants. So here's a coal layer, this black layer. I had a piece here with me, coal. And above and below it are sandstone and shale. The coal layer marks a place where you maybe have a swamp or a wetland area, and then the sandstones and the shale would be telling us that there was a swamp in place, and then sea level rose up over that. So these are good indicators of changes in sea level over time. A chemical sedimentary rock, so this is not associated with biological activity necessarily. These are molecules that are going to precipitate out of solution. So water that is hot is going to have dissolved ions in it, and when it cools down and the pressure changes, you get deposits of these. This is called travertine at a hot spring. In the case over here on the right is a like the bottom of, say, Death Valley, where you have a basin that water, the only way water gets out of that basin is through evaporation. So over time, those salts that are washed down from the mountains accumulate in that basin. So here is travertine. Travertine is calcium carbonate, and it's going to be deposited at the surface at like these, where groundwater gets to the Earth's surface, and that dissolved calcium carbonate is going to react with bicarbonate. The CO2 expelled into the air causes the CaCO3, that calcium carbonate or calcite, to precipitate out of solution. So it happens in these thermal hot springs and similar chemical reaction in caves. This is dolostone. Dolostone is a carbonate rock like calcium carbonate. This calcium carbonate was underground, and we think that the circulating groundwater had magnesium in it, and the magnesium replaced some of the calcite in that chemical formula. And so a dolomite is really similar to a calcite, but has Mg in that cation spot. Not all of it's been replaced, but some of it. Okay. Chert can form when those plankton, those microscopic organisms die and fall to the seafloor. Bug. It can also just precipitate out a solution. So I held up earlier, I'll do it again, a piece of petrified wood that's like in the image here. And petrified wood is going to occur when that silica-rich water essentially deposits chert in the pore spaces. This is the bark of the tree trunk, but it's been replaced by chert that was flowing through it. There's also some nodules here. Those nodules formed in a cavity in a space within the pre-existing rock.